Hi. So I guess I should probably just quickly introduce myself. So like most of us here, I think we've kind of found ourselves into data science one way or another. So I actually started off as a design engineer. And even though I work as a data scientist now, I kind of find it hard to let go of what I used to do a little bit. So some of these examples that I'm going to go through is kind of my attempt to sort of hold on to my past, but also where I think data science has a lot of application in design, both engineering design, but also product design. So hopefully I can kind of illustrate that to you guys today. So the core of this talk really is it kind of centered around these three examples. On the left, this is, you might not be able to make out what this really is, but this is actually like a shrouding which goes around a propeller on a drone. So we had a particular use case where a client wanted to use an off-the-shelf drone to do some structural surveying. However, they had quite a lot of constraints around health and safety, and they wanted to be able to kind of shroud the propeller. So the design problem here is how can you introduce this new component into the drone and not kind of sacrifice the performance. So this is like kind of like an engineered design that is trying to like optimize to make sure that it doesn't impact the performance of the drone itself. The middle example, that's actually a skateboard shoe concept, and this was the goal of this project was to optimize a shoe to satisfy a particular skating style. So I'll talk about this one in a bit more detail, but that's also an optimization problem. And the third one is a render from a smoke animation. So in this case, the optimization problem is to come up with something that looks aesthetically pleasing. So these three all have a few things in common, but they're very, very different. I guess the first thing is that they are all optimization problems, and they're actually all the result of Bayesian optimization. So that's going to be the key theme as well, is Bayesian optimization. I wanted to talk more generally around Bayesian methods, but I realized there's quite a lot to talk about in 35 minutes, so I've kind of restricted it to Bayesian optimization. They have another thing in common in the sense that actually understanding the performance of any of these things is actually quite a complex and expensive task. So in the ducted fan example, to actually evaluate that and understand the performance took 4 hours of computational time. For the shoe, to understand how the grip interacted with the skateboard, and also to sort of better understand the cushioning and how the skater likes the cushioning and how he feels about the cushioning, kind of requires, again, a bit of computational simulation time, but also prototyping, simulation, testing, and all these things are expensive to do and cost a lot of money and time. And a third problem, well, it's kind of up to you how long you want to render an image for and what sort of resolution you want to get. But kind of to generate an animation at quite a high frame rate will take a few hours at least. So I kind of really want to just introduce the problem from like a designer point of view, but what you'll see here is actually the Bayesian optimization. So I don't want to make any assumptions that anyone's seen Bayesian optimization before, so I'm going to start from the beginning. So this grey curve, which you might be able to see, but it doesn't really matter because you're not supposed to be able to see it. This is like an unknown function that you're trying to optimize over. So in this case, let's assume this kind of models the drag of that ducted fan that we looked at. So what we want to do is we want to basically come up with a design that minimizes the drag. So we need to make some sort of decisions as to what parameters to evaluate to get there. So on the x-axis, we've got like a design parameter. So we can change this design parameter, which will change the geometry, which will then impact its performance. So what do we do? Like what designs do we evaluate to optimize the performance of this fan? There isn't really much data science going on right now because there is no data. So the best thing I can do is I've just got this straight line going through 0. And I haven't got anything to actually like fit a model to or really understand what's going on. So the first thing we need to do is go away and actually take some measurements. So this is kind of like an initial set of samples. So I've evaluated this design at a few different geometries that are given by the x variable. I've chosen 5 evaluations in this case. You can kind of do this randomly, but it kind of makes sense if you try and space these out a little bit. There's only 5 evaluations there, but this took 4 hours to run and actually evaluate the performance, so that's still 20 hours worth of work. So you can start to see how it's quite an expensive process to actually make improvements on this design. So what do I do about making improvements? Like, I don't know. You can see there's an area on the left-hand side which I haven't actually evaluated yet, so do I go over there? There's a region around x equals 0.6, which is kind of the best design I've seen so far, so I could decide to kind of exploit that region. And, you know, this is the kind of decision that you need to make as a designer. What do I evaluate next? And this is where Bayesian optimization is super helpful. You tend to use something called an acquisition function, and you can construct this acquisition function in any way that you wish, but it's quite common to sort of try and balance the idea of exploring new areas and exploiting areas that you already know perform pretty well. So I'm going to make use of this acquisition function. This acquisition function is based on this approximation of what's really going on, which is this blue line. So I'll just add a new point at the point where there was this maximum kind of expected improvement. And that just took another 4 hours. So what do I do next? I just sequentially iterate and keep maximizing this area of expected improvement and then adding and running a new design there. So after about 10 evaluations, I've kind of found this kind of minima, so I've minimized the drag of this design. That's still 40 hours worth of work, so you know, even though there's very few data points, it's still an expensive, time-consuming process to do that. Okay, so I kind of shown the process, but I wanted to make sure that anyone that is completely new to Bayesian optimization had a little bit of an understanding as to how it's working. So the next few slides is just to sort of give a little light introduction about what's going on here. So there's 2 key components to what I just showed you. The first was this model, and it's quite common to use Gaussian processes in Bayesian optimization. You don't have to, but it's quite a common thing to use. And the second thing was the acquisition function. So the first thing to introduce is the Gaussian process. And there's lots of really sophisticated libraries to do it. And I wouldn't necessarily encourage you to write it up yourself, but to show you that it isn't that complicated, all I'm going to use is NumPy and matplotlib to plot it. So the first thing to introduce before we talk about Gaussian processes is random variables. And the reason for talking about this is because a Gaussian process is just a generalization of a random variable. So hopefully if you understand random variables, Gaussian processes aren't too difficult at all. This is actually a multivariate random variable, multivariate normal random variable, and that's characterized by a mean and some covariance. And I mean, I should say what a random variable really is. A random variable is a variable that just doesn't take a single value, but it can take a range of values. So each time you evaluate what that variable is, you'll get a different answer. The answer you get will be based on some, characterized by some sort of probability. And this is how you can construct it. This is a bivariate, so there's 2 variables here. So you kind of create your mean, your standard deviation, you create this covariance. And a really popular way to just visualize this is just to take realizations and see what you come out with. And that's what this random variable looks like. I'm guessing this isn't too dissimilar to what people have seen before, so hopefully everyone's still with me. But what you sort of see is both x1 and x2 vary between -4 and 4. They kind of have a central tendency around 0. But there's also this sort of structure to it where if I increase x1, I'm also likely to have a higher value of x2. If I just project all that data onto the x-axis, onto the axes, you get what is like the marginal distribution, and that's kind of not really giving you any new information really to what I just told you. But another way to visualize this is to sort of plot them on vertical axes and sort of join the lines between the data points. So if I just take any one of those dots, I can draw a line between, two vertical axes. There's nothing actually in the middle, but sometimes this helps people visualize how this can start to generate like a function space rather than just a variable space. Okay, so this is the useful bit. So when I make an observation about one of these variables, it actually gives me quite a lot of information about the other variable. So if I sample, or if I observe that x2 is equal to 1, then it actually reduces my uncertainty about what x1 is. I now think that x1 is likely to be greater than 0, and I'm kind of a little bit more certain about it. And that's the conditional distribution. Another way to think about it is out of all those random samples that I had originally, if I say x2 equals 1, I can just throw away all the samples that don't equal x2 equals 1, and it's just the ones that are left, basically, in some way. And then that's the distribution you get. And then if you visualize that on the right-hand side, you can see I'm really certain about x2. And because I've made that observation, x1 is now between -2 and 3, rather than being between -4 and 4. So this concept of having an observation and then learning a little bit more about what's going on around you is just the concept that you would apply to a Gaussian process. And they're pretty much characterized in a really similar way. You just have a mean, or a set of means, and then you have this covariance function again. And you can construct it like this. In this case, the mean is a function of x, but it's actually just equal to 0 everywhere. And my covariance, you can kind of do what you want. There are some rules. You have to kind of correlate your data points in some way. And there are a few rules you have to follow, but you can be pretty flexible about it. I'll try and show you a little bit of an example in a minute. But basically, I'm just taking all my x's and doing a pairwise comparison and taking the square difference and then doing the exponential of it. And just like before, I pass this mean and the covariance into this random number generator, multivariate random number generator, and I can generate some realizations. The difference now is that I'm not just taking a realization of a single data point. I'm now taking a realization of a function. So a Gaussian process, a realization is a collection of functions, basically, and then you can just pull the functions out as you please. If I increase the number of realizations, I have no data yet. I'm just drawing realizations from the Gaussian process. So you can start to see how this is kind of centered at 0, and then it's got this plus minus 1 kind of standard deviation going on. Like I said, you can kind of do what you want in this covariance. So I can start adding a bunch of hyperparameters, and this can kind of help me control what's going on a little bit. So in this case, hopefully you'll see a difference. So basically what I'm saying here is, as I move away from x, well, as x moves away from one another, y changes more rapidly. So if you've got a more rapidly moving function, then you can actually model it by including these sort of hyperparameters. There's other stuff you could do. So rather than assuming a 0 mean, I could assume a mean that does actually change of x. And that's kind of then baked in a linear trend into my Gaussian process. So you can play around with this covariance and this mean function as much as you want, really. So what happens when I have data? Well, the same thing happens as what it did with the multivariate random variable. And when I have data, you kind of create a conditional Gaussian process, and then you basically see that it affects the information around it. Another way to look at this is out of all those realizations I've had before, I've added a data point, and all the realizations that pass through that data point I keep, and all the realizations that don't pass through that data point I throw away. And that's kind of like the intuition, I suppose. You know, I can start adding more data points. And it's quite nice properties in the sense that I'm not modeling the mean in any way. I'm just kind of taking these realizations, and out of it, I'm kind of getting a distribution that is quite natural to quantify uncertainty and also give you like an average outcome of the model that you're trying to model. I should point out you don't have to be doing realizations all the time. All this can be done analytically. It's just to try and show some intuition about what's going on. So what about the acquisition function? So in Bayesian optimization, you would have some data, you would fit a Gaussian process or some other model to it, and then you would use that model in a way to help you decide where to evaluate next. In this case, I want to make improvements on my best design found so far. And in this case, let's say we're minimizing. So my best design found so far is around 4.5, and it's equal to about -1. So a really simple acquisition function is to look at all the realizations that are below -1 and divide it by my total number of realizations. So you can see that there's no realizations over on the left-hand side that are below -1. So I've got 0 here. You can see over on this right-hand side, there's a whole bunch of realizations that go below -1. And then I can just kind of work out the probability of actually being better than my current best design. This is just heuristic based, so this is all like not smooth and nice, but if you're doing it properly, then this would just be all analytical and be nice and smooth. It's really important to note, like, these acquisition functions you can kind of manipulate to do what you want. Like, if you don't think you've got like this multivariate design space and you've just got like this nice convex problem which just has a simple direction to find improvements, then you can just use pure exploitation. So you just kind of take the point that you know is good so far, or what your model predicts to be better, and then you just exploit in that region. Another option is pure exploration. So if you actually want to build like a globally accurate model and then you want to use that for like either visualization or sensitivity analysis, then you can actually just keep updating your model in the region that you've got maximum uncertainty or really large uncertainty, so basically where I haven't already sampled. You might have constraints, you might have multiple objectives, you might have noisy functions, you might have stochastic functions, and all these things can kind of be built into this acquisition function, which always kind of helps you make improvements on your current best designs. I imagine most people are kind of familiar with this in the sense of hyperparameter tuning and machine learning. It is the same thing, but I'm applying it to design problems rather than machine learning problems. Right, let's go back to the case studies, because that's what I really wanted to sort of illustrate today. Okay, so this is that ducted fan that goes around the drone propeller. So like I said, when we introduce this new component to the drone, we're going to impact the performance of the drone. We're adding weight. You're going to have to increase the power requirements. There's a whole bunch of stuff you need to start thinking about. So you need to kind of design this thing quite carefully. And the idea is that you're kind of adding this thing which should theoretically mean that you need more thrust to keep this drone up in the air. But if you design it carefully, you can actually generate thrust from the ducting itself. And the way you kind of do that is you pull the air through it, and if you can get a nice region of kind of negative pressure, I guess, on the front leading edge, you're kind of causing a component of lift as well. So that's what we're really going for here. But it's quite a challenging problem in the sense that the geometry is so subtle, it has a big impact on what the performance of the actual ducting would do. To try and illustrate the problem a little bit more, this is like a cross-section of the ducting. So imagine that duct. Imagine me taking a slice through that plane. The line in the middle is kind of where the propeller would be whizzing around. And then I've got a bunch of design parameters. So these parameters are the ones that I need to find a combination of that gives me the best performance. So there's some really, really obvious ones. So this is basically, oh, I knew that was going to happen, don't worry. I haven't quite got the knack of these little widgety things. Yeah, so this blade to chord ratio basically kind of increases the size, reduces the size. That's kind of one parameter I can play with. So maybe in that first example I showed you that just 1D example, maybe it was just the size or something like that. Some of these are really subtle, but hopefully you can sort of see the angle of attack, so that's kind of like pulling it inwards. Some of these are more to do with the actual the surface of the geometry, so some of these are quite obvious. That kind of makes things a bit fatter. Yeah, anyway, you get the idea. So basically I've got 8 parameters that I need to play around with to come up with a really good design. The problem is it takes 4 hours. Each time I make a change to one of these sliders and rerun, I've got to wait 4 hours to get a result. So the kind of system that we put together for this is all the optimization engine is in Python, and that is that Bayesian optimization routine that we're talking about. That kind of like adds a few designs to a queue. The 3D geometry is created in a program called Rhinoceros, and this is a really nice program because it does have a Python API. It is Iron Python, so it's not ideal, but as a Python developer, it's really easy to automate the geometry generation and turning that into something which you could then send off to an analysis package. So in this case, what we're interested in is that simulating the flow, the airflow over that duct. We're interested in simulating the blade spinning and drawing the air through it. And to do that, we're using a computational fluid dynamics package called StarCCM+. And this is the bit that takes all the time. This is the bit that takes like 4 hours to run. And then when we get the output, we can then feed that back to the Bayesian optimization engine, and we can then decide what to do next. So just going around this lower loop would be what you would just normally do in hyperparameter tuning, for example. But what we wanted to do is, this is an engineering design problem. There's engineers that study aerodynamics. We don't want to just let a machine decide to do everything. So having the user in the loop, having a human being able to influence the direction of the optimization routine is really important. So we built this little web app, which means that the user can actually monitor what the best design seen so far is. So, after 4 hours of running, you can then see, and it's like, oh, has that got better? No, let's leave it for another 4 hours, see what happens. If he sees something that's really cool, but he thinks, oh, actually, from my domain knowledge about this, if I just slightly change the leading radius or the tail geometry a little bit, I can resubmit this back into the queue again. And what actually happens is that's then picked up by this Gaussian process, it's then picked up by the acquisition function, and you're influencing the optimization routine by having this human in the loop. And this is kind of what happened. This was quite a long process, so we ran it for like 120 iterations, which was like 2 weeks, I think. It was running for a long time. So having this web app was also quite useful because you could actually like check in to make sure it was actually still running. And I can't remember what my initial set of examples was, but I think after about 60 or 80, maybe that's when it starts using this like acquisition function expected improvement. So you kind of start to see it jumping around a lot less. The contour plot is like the current best design, so that's not updating on every iteration, that's staying as what is our best design. So if we run out of time, run out of money, that's kind of what we're left with. And you'll notice that the objective function is the combination of the propeller thrust and also the duct thrust. So you can sort of see as this optimization routine goes up, as the total thrust goes up, it's actually the duct thrust that we're increasing. So that's because of the geometry of the ducting itself. I won't leave it to the end because I don't want to run out of time. Okay, so that's like a really solid engineering example. But I said I was going to talk about product design as well, which isn't always so engineering-based. So this is that skateboard shoe concept. So we really focused on 2 things here. One was the interaction with the skateboard, so the grip, and the other thing was like the cushioning of the shoe. This is actually the final design, but I'll show you how we got there. So the idea really, this is just a concept. So it's kind of like, as a skater, I could go onto a website, I could put in my shoe size, my weight, my kind of skating style. So some people might want to know what the skateboards are doing all the time. They're doing like really subtle tricks while someone's doing really big tricks and they need like loads of cushioning in their shoes. And there's a whole bunch of things. They could come in, they could sort of tune it. And then the optimization problem is to go away and design them the perfect shoe. So the first thing we played around with was the grip. So this is kind of like a small section from the outside of the sole. And there's a bunch of parameters which will manipulate the geometry. So you can kind of see that one parameter is kind of changing it from like these like tessellated squares to these hexagons. One parameter starts manipulating it in the sense that it kind of becomes less, it protrudes less. And then it kind of makes the outside protrude more. You kind of get the idea. So in this case, we've got 5 parameters which manipulate this geometry. And we did the same thing again. Rhinoceros was used for this 3D geometry. There's also a really cool package called Grasshopper, which is what allows you to parameterize your geometry really nicely, and then that can actually be controlled by Python. So you can kind of imagine that geometry being manipulated by a bunch of sliders, which you just control using Python. We use a different package for the simulation here. This is HyperWorks. But the same concept applies. So we kind of come up with this objective function based on these user preferences, and then we optimize. And again, this is kind of like what happened. So you can sort of see the variation in the different geometries of the grip pattern. I'm going to run out of time, so I'm going to do it. This is, the other problem was the sole. So, or you know, how the sole is constructed for like the cushioning. So we kind of came up with this sort of parameterization, which is kind of based on these Voronoi tessellations. And what you could do is, in the areas of higher load, higher pressure, so kind of on the balls of your feet and then your heels, you can kind of have more tessellations. And you can kind of take points away and add points and move them around. And you can kind of control how the load is kind of distributed across the shoe. This is actually in the 3D volume. So this is like, I don't know if you can see it very well. But anyway, you kind of move one of these center points of the Voronoi volumes, and you kind of change the structure of that kind of cushioning, that sole. So by basically parameterizing this in such a way, you can like manipulate all these center points, and you can kind of get the perfect cushioning, in theory. So, yeah, okay. So I said about product design not quite being like engineered. I really wanted to kind of show an example which didn't require any engineering, simulation, complicated fluid dynamics, structural analysis and stuff. So I kind of wanted an example which is purely based on what I thought looked cool. So how do you optimize something that you think looks cool? I mean, it's really difficult, because if I say something looks cool, someone else would say that looks rubbish. But basically what we need to do is we need to kind of like infer this underlying utility, like how do I feel about something? As I change a parameter about this object or this simulation or this animation, how do I feel about it? I mean, that's quite a challenging problem. But to show you that I think it can be done, one way to do it is actually not to present like single items to a person, but present pairwise comparisons. So your data set doesn't become a set of inputs and an output. Your data set becomes pairwise comparisons with which one they preferred. And from those pairwise comparisons, you can kind of, there's a law called law of comparative judgments that you can use to try and understand how they feel about this object. So I'm going to do it for this picture. So I'm basically just going to select which picture I prefer. Yeah, still like her. Oh. You can't see it on that screen, but there's a little bit of blueness, which is quite nice. I quite like the pink face. But can you see how this is kind of converging? So this is based on my selection of what I prefer. This is now converging towards a design which is kind of maximizing my utility. and trying to show you what that looks like behind the scenes. I purposely set this up, so I took the original image, and I changed the contrast, and I made sure it was centered around 0.5. So all I've actually done is converge back to the original image again. But you can sort of see how I've maximized it. Using the expected improvement and this Bayesian optimization routine, I've actually converged to this region, which is close to 0.5. That's kind of what I was expecting to see. To show you on a slightly different example, this is what I referred to at the beginning. But this is like an animation. And like I said, this takes a bit of time to run and compute. And I arrived at this final design in exactly the same way. So I did pairwise comparisons of different animations, and I basically converged on the one that I personally thought looked quite cool. I'm going to give this a go, because there is a bit of time left. It's risky. Let's see. So that's, Blender is a tool which people use for 3D visualization and animation. And it's really cool that you can just simply control it using Python. And this is running that smoke animation. When you set up this animation, it is completely pointless, by the way, but it's just trying to prove a point, I think. Right. There's a whole bunch of parameters around the smoke, like the physics of the smoke. Yeah, like this density, temperature difference, velocity. There's like initial conditions around the velocity of it and things. So these are all parameters that you can change, and that influences what this animation will look like. I did it in the same way. So I used this Python optimization algorithm. I generated the animation using Blender, saved the outputs, and then in this case, obviously it required me as a user to interact, so I just used like a Jupyter dashboard thing to do that. And these are some of the comparisons that you made. So some of them are like little dissatisfactory little puffs of smoke, so they definitely didn't go through. Some of them like reached the domains of the simulation domain, like that one, so that's not particularly pleasing. So basically doing these pairwise comparisons, I've kind of converged on the simulation that I was quite happy with. Okay, I always go faster, and I'm 2.5 minutes faster than I normally am. But basically that's the end of the talk, so if anyone has any questions.
Hi. You spoke about using engineers' domain knowledge to inform the process. Did you have any luck using informative priors, or did you mostly stay with uninformative priors for the Gaussian process?
Yeah, I mean, there's a whole bunch of stuff you could do. So I think one of the reasons I kind of wanted to show how you can manipulate the kernel function and that mean function is because that's one way you can embed some sort of domain knowledge about what's going on in the background. You do see that a lot more in like physical-based like domains that are using Gaussian processes. I know in machine learning you would tend to just use zero mean functions everywhere, but actually if you go to some other conferences that are around geophysics or anything else using Gaussian processes, there's a lot of domain knowledge bedded into how you're constructing it in the first place. So yeah, I think I went for injecting the human in the loop a little bit, but actually you could do a lot more up front to make sure that's the right approach instead.
Other questions?
Thanks. You mentioned, I think halfway through, there was one iteration you switched halfway through from exploration to exploitation in the algorithm.
Yeah.
How did you, in terms of the different examples and things that you tried, what kind of rules of thumb or lessons did you learn from the different meta rules for selecting your next point to evaluate?
Yeah, so, I mean, it's difficult to have a one-size-fits-all, but there is a lot of things that you can do which are actually quite straightforward. So it all depends on how long your simulations take and what your total budget's going to be. If you have an idea of what your total budget is going to be, there's actually some papers out there which would recommend saying that you should use your number of dimensions times 10 as an initial sample, and you don't always just jump straight in for expected improvement. What's actually really beneficial to do first is a few, like maybe n times 10 sets of just exploration, and then you could just do exploitation, and you might achieve something very similar to what expected improvement is achieving in the long run. But if you can afford to do that, I probably wouldn't go expected improvement straight away. I'd spend a bit of time exploring, a bit of time exploiting, kind of mix it up, do what you want, I suppose. But yeah, it's hard to say. If in doubt, use expected improvement, basically.
Yes, the type of techniques you've demonstrated, what really prevents them from converging on local optima that may not be necessarily the best? So, for example, when you did the interactive interactive evolution by aesthetic selection, that's one way of describing it. How do you know that if you were to start again afresh, you would converge on the same picture?
I don't know. For that particular aesthetics type problem, I don't know, because I've only just started looking at it, and I think the noise of someone saying they like something and then asking them again and then them changing their mind is going to make this quite difficult to converge, probably. But in like the general setting, if you're using interpolation, you've got no noise, then expected improvement, in theory, is guaranteed to converge, because wherever, in the areas that you have no data, there's always going to be a probability of improving in that area because you've got some uncertainty. If you have noise, that's when it starts getting a bit more complicated. If you've got a stochastic function, that becomes even more complicated. So there's like layers of complexity. I think in the kind of human in the loop, I don't know how trustworthy humans are, but I'd like to get them involved, but maybe get rid of them again one day. I'm not sure. I don't know. I'm sorry.
Hi. How do you go about selecting parameters for your kernels?
How do I do it?
Yes.
Oh. I take the lazy approach usually and just go for like a squared exponential kernel function. But
the parameters, not the kernel.
Oh, the parameters. Oh, okay. Yeah. So I just do log likelihood normal and optimize over that to get the high parameters. But if I was going beyond that, like, because all these are quite straightforward problems, like examples, so I wouldn't necessarily do that. You can do a full Bayesian treatment of it if you want. You know, if you use a library like GPFlow, that's what I'd recommend. Then, just you can do whatever you want, variational inference, all sorts of stuff. So, but in this example, it was just straightforwards. And it wasn't even a global optimizer. It was optimizer. It was a multi-start local optimizer I used to tune it.
So. With the duct you were doing the optimization on, in choice of features you were using for the trade space, were you optimizing for a static case, or were you also trying to think about how the duct, when it's being used by the drone to move through the air, is going to be adding a drag or weight, that sort of thing?
Yeah, so I guess the drone problem, well, to be honest, it's not just the drone problem, it's any problem. There's lots of other disciplines that you would probably want to involve. So, you know, I was talking about adding that component, increasing the weight, and I was trying to counteract the increase of the weight, but I haven't actually worked out how much it would weigh because I haven't worked out what the structure would be, what materials it would be, all sorts of stuff. So that parameterization was very specific for a particular flight regime, and it was because it was for a surveying vehicle. It basically had a certain flight requirement to be rising at a certain velocity and coming down at a certain velocity. So I didn't really take into account all the idea of crosswinds and the structure and the weight and all sorts. But, I mean, it's a really valid point that any problem like this is very multidisciplinary and there's lots of stuff to sort of think about. But that parameterization was just purely to try and optimize over that flight regime. Does that answer the question? Or?
Yeah, maybe we can talk about it later.
I shouldn't have finished so early. I should have dragged it out. There's too many questions.
Hi, just a question regarding the CFD. So, because currently you use a star package, do you see moving forward that data science could be complementary, if you want, to CFD, especially when you have cases like particle modeling where you can always apply that to your smoke testing, or when you're going to have a porous surface modeling again, where you're going to talk about particles in terms of libraries, in terms of...
Do I see machine learning being used in simulation in general?
Yes, in computational fluid dynamics simulation, are complementing that.
Yeah. In fact, there's a guy that we work with who had a master's project which was using neural networks to help enhance kind of like... And there's a whole bunch of stuff like compressive sensing is really popular at the moment in that sort of domain. So I think there's a whole load of stuff that you can do to learn. Like, I guess in one way you could think about this as it took me 4 hours to run every simulation. And I was kind of fitting a model to the outputs of those separate simulations, but I could have an enhanced simulation which has some machine learning inside, which returns me a result in a few minutes, right? So, yeah, you could apply it to the simulation side as well. I don't know much about it, though, unfortunately.
Okay, thank you all for attending, and thanks, Jay.